joining me, I have the wonderful Dr. Satyam Priyadarshy, who is the Technology Fellow and Chief Data Scientist from Halliburton. Now, this next session is going to be brilliant because it's going to be all about the evolution of quantum computing and the role that machine learning can play in the evolution of that technology. It's going to be fantastic. Like I say, we're leaving plenty of time for questions, so make sure you get those in. Without further ado, over to you, Satyam.
Thank you, Catherine. Good morning, good afternoon, good evening, depending on where you are listening from. First of all, it's a great honor to be here. And I would love, as Catherine said, to talk about quantum computing. This is going back in the history for me. I used to be very active in the space and formulated some interesting challenges and solutions for very complex problems, but they could not be computed because the computing power didn't exist even with high performance and parallel computers. On my introduction screen, there is one equation that I have put, and someday I hope that in my lifetime we are able to resolve this for a three-dimensional system. That will be very interesting, and I'll talk more about it. So what happens to the impact of quantum computing in the post-Industry 4.0 era? So as we all know, we are in Industry 4.0 era, so we'll talk about some of those things. First of all, let me thank the organizers for inviting me, as well as AI Champions team, and then more importantly, all of you who are listening to this, and the most important, the people who actually enable me, encourage me, and empower me to actually do these kind of talks and share my experiences. That includes my PhD advisor and my primary school teacher. I happened to meet them last year at the same time from two parts of India, but in the same city. So which was I feel I'm very blessed. Second is my family, which allows me to travel when the travel was allowed. And of course, over the years, I've been a lot of collaborators I've worked with in Australia, India, US, and many other countries. And even in corporate world, I've built fantastic teams I worked with to actually play with data at very high scale. And of course, my parents, siblings, their families, and friends and families, because when I travel, I have to really spend time to find some good food, and that's where I go. So with that, just a brief background why I think I want to talk about this and why it is important. My PhD was in quantum chemistry. I solved for a biophysical problem using quantum mechanics, and in fact, at that time, we were able to only solve numerically some one-dimensional problems because the computational power didn't exist. And it has so much relevance to today, especially when we are talking about energy transition landscape. And of course, some of this work has been written up in various magazines and others. I've spent time in academics as well as in the industry in multiple areas, nanotechnology, of course, digital transformation, AI, ML, and now, of course, I've been recognized as the first chief data scientist of the oil and gas industry. So very diverse kind of experience that I have. So I think quantum computing actually plays a role in all these areas that I have actually had fun over the last couple of decades. So what are the couple of topics that I want to talk about? Is just what Industry 4.0 era will look like, right? How is it dependent? It's mostly one thing that we know, that the data growth is inconceivable for whoever wants to predict. I think that whoever builds that predictive model, that will be awesome, but I don't know whether that can be done because the emerging technology is moving too fast, becoming too small, right? So in case when the data growth is like that, how do you actually build insights for actually strategizing the business? And that's where I think the role of quantum computing becomes important, because it's a new paradigm. And as we all know that beyond Industry 4.0, it will be mostly human to machine interactions that will become important. Now, if you really want to look at this picture on the left-hand side, that's a picture of a chloroplast organelle inside a plant leaf. And that is the energy engine from the nature. It has so much relevance in today's times, and actually to learn how we can actually try to leverage various computing paradigms, the various pattern recognition terms that exist, if we can actually understand what happens inside a chloroplast, right? If you look, the picture, I don't know how good it is on the screen, but it is a perfect, those who want to study design thinking, they can look at it, how nature has designed this, that this organelle actually produces energy at the highest efficiency possible. Whereas, as we all know, the solar cells that we human design have an efficiency only of 15% and maybe 25% in the lab, but they have a life of less than 25 years, right? And requires a lot of maintenance, but plant leaves can generate energy. So think about it, design thinking principles that we can learn from here, the organization of material inside it, which allows you to actually move electrons at a very high speed to generate energy. So this is why it's very important to understand this. Now, if we come back to what we understand as human beings, the Industry 4.0, I talk about this, that it is all about how our data and digital maturity increases in an organization or in any field, and so that you can generate economic value. Most of us are engaged in this simple left-hand box, building some innovative solutions, but many industries are very slow in adopting emerging technologies, as well as really increasing their digital maturity. Of course, since the beginning of 2020, for multiple disruptive events, there has been renewed interest by many organizations to actually transform, which is a good sign that we are walking towards on the right-hand side of this curve. And then eventually, if we actually become good at adopting these new technologies or emerging technologies and increase our digital maturity, we can actually build disruptive engines for our business. Otherwise, many of the businesses will be disrupted by other players. Now, this is very critical, because if we stay in this left-hand bottom left box forever, then many of these businesses will not probably will not be visible after a few years. And that have been very true if you look at the last 5 years of retail industry, what has happened to them. In fact, about 7 years back, I used to consult before I joined Halliburton in this space, and I used to tell them that it is time to leverage these emerging technologies and do real-time resource optimization. And most of the people would say, analytics people would say, "Oh, we know how best to look at our data." And I said that if we don't look at it, the companies won't exist. And that's what happened 5 years ago. Many retailers started shutting down because they couldn't compete, because they didn't walk this axis. They didn't walk this axis towards the disruptive growth. And this will happen to many other industries. Because as we see what has happened in last, say 10 years, if you want to look at it, a lot of new computing paradigms have come up, right? We all talk about cloud, fog, and edge computing. These are great platforms to do computation, but they are also a great source of data that is being generated, whether it is for yourself or whether it is for your ecosystem, but they have significant amount of data from which one can learn. The concept of IoTs or industrial IoTs is a reality now, and almost every industry is trying to implement them in some shape and form, but some are going faster, some are going slower, and those who are going slower, they tend to remain laggards in adopting the digital and in maturing their digital maturity, right? And of course, the term I like is immersive reality, that is augmented reality, virtual reality. But if you think of it, what we really want to do is really immerse in that reality and actually execute on it. And this is something being done in some industries especially when it comes to, for example, aviation industry. People are building these. In earlier days, it would have been a very expensive training program for pilots. And of course, there was offline version of those training. But today, leveraging this immersive reality, the training programs are actually as if you are sitting inside the plane with all its vibrations that may exist in real world. And that is the power of these emerging technologies. But as a result, it generates significant amount of data that can be leveraged, right? The other one is software defined. Almost everything will become software defined, as we can see amount of work that we do today, whether it is the routers, the switches, they will also become software defined more and more. And of course, then the last part is cybersecurity, which is both in terms of personal cybersecurity, at home cybersecurity, the corporate world, and of course, in the platform world as well. So if you look at it on the mobile world that we are so used to, this itself is going to grow exponentially because even if we know in last 2-3 years, and even since January when the COVID disruption started, the ransomware, the phishing attacks, they have significantly increased at a personal level as well as at the corporate level. So one has to be really watch out for these things as we include. And this requires significant amount of computational resources as we move forward. So if you look at it, what happens when Industry 4.0 is more mature, that means we would have a universe of where human to machine interaction, machine to machine interaction will become actually at a consumer as well as at an industrial scale. And that requires, for efficient use of it, that requires self-healing devices, that is, or the machines that heal themselves, so to say, or can heal each other. But these will be based on what we call futuristic materials. And all these things can be developed if we actually know how to actually take advantage of quantum computing paradigms. So if you look at it, how do we compare these things, right? What are the computing paradigms? The one that we are always known is the today's analog computing, right? Of course, the brain we know, which is the other extreme of it. That means it's good at so many things. Then, of course, the modern computers that we talk about, that we use every day, and then the quantum computers. So if you look at it, it's a simplified version of the computing landscape. But if you look at it, each one of them have a role to play. None of, whether we are using machine learning, artificial intelligence, how good are we in pattern recognition for certain things we do, we're better at scale. But if you compare it with the human brain, we are still not there, right? Only certain things we can do, but not everything that a human brain is capable of. Because if you think of it, human brain is a parallel distributed, quantum, digital, bit-driven computer, basically. And it has infinite memory, so to say, as well as infinite processing power. This is why, when we were talking about cognitive computing 4 or 5 years back, we haven't seen a real cognitive computers because to build a cognitive system like a human brain, let's look at some building like an animal cognition system, right? My classic example is we are still building self-driving cars. But if you were from India, you would know that the bullock carts would run in the night and they never had an accident. The bullocks were much more smarter, whereas our self-driving cars are still not reached to that point. So cognitive computing is not there. But the advantage that we see with quantum computers is that we can actually scale it. Once the hardware, so to say, in brackets, hardware is available at scale, we can actually scale the computing power very, very much with quantum computing. So I'll give you some examples of that. The reason is that as we build, we are living in a very complex landscape. And if we just talk about the energy transition landscape, it's very complex itself. So it doesn't matter whether we talk about energy landscape, manufacturing, but as more and more of these computing paradigms are used, you will build a landscape which is complex. Typically, most computations we would do, we will get trapped in one of these local minimas, whereas our goal is to find the global minima in this landscape, right? That means, or a highly optimized energy transition landscape that we want to do. And this is suddenly needed for almost all energy companies. It doesn't matter oil and gas or renewable energy or geothermal, doesn't matter. We are all part of this big energy transition landscape, which is pretty complex, right? When we look at that local minima versus global minima, because because we can always find zero. If you look at the bits, we can do 0 and 1. We can end up in one of the local minima and can stay there. But when we start talking about qubits or the quantum bits, this is when you can actually navigate the whole landscape and go and find your global minima. And that's where the bits to qubits becomes a transition that is needed. Right. Well, if we are talking about qubits, one really needs to talk about Schrodinger equation, and I'm not going to give a lecture here on quantum physics or quantum chemistry, but it's a particle wave duality that we talk about, and that is very important. So, but if you compare it, that if you want to talk about two state in a typical digital computers, the two numbers 0 and 1 will give you state 0 or 1. But in the quantum world, it becomes qubit, and then you need 2 to the power n states, and so that will be 4. So if you look at it, if you want to describe two things, then you can actually look at these pictures, and you can see that you have a superposition of these 4 states to describe your two states, so to say, right? And this is what gives you the spectrum. If you can visualize that how these just 2 state can be scaled onto that energy transition landscape picture that I showed earlier, when you have x number of bits, you can actually look at the spectrum in a much more rigorous manner. And this is the beauty of quantum computing. So the other advantage that, with every single qubit increase, you actually increase the computing power by, you actually double the computing power, which is interesting. And if you had a 64 qubit system, then you are actually talking about 2 to the power 64 numbers, so to say, or in a quantum state. That means if you think of that picture that I showed you earlier, you have spanned a much larger surface of that landscape. So where does the quantum disruption can take place? Some of the things are well known in the industry, and I have association with at least almost all of these 4 areas with these 4 areas. One is the computational chemistry, where I feel that the problem of inverse molecular design is critical. The drug discovery becomes very important, especially in COVID times. We should be looking at the vaccination part of it. If we had that much of computing power, we could have leveraged. Of course, nanotechnology is another area. I've done some work in the area of nanowires, and I think that is an area there where it can be advantageous. And of course, the energy landscape, as I said, which I call oil and gas 5.0. And of course, in the business world, we can talk about cybersecurity space, where we can talk about self-cleansing intrusion tolerance kind of a system, which can take advantage of very high computing powers. Right. So 3 case studies at a very high level that I want to cover, since I've been told that we have only 10 minutes to go. One is, of course, the renewable energy area, right? Especially solar cell efficiency, as I mentioned in the very beginning. The human-created versus nature-created efficiencies are so different. Of course, there is a lot of work going on in R&D labs, and it's actually very, very powerful and very meaningful. And hopefully, in the next couple of years, we should see some very interesting bio solar cells, or you can call them quantum solar cells, that will come out of these labs and from various experimental groups, which is very important. Then we, of course, the nanowires and the nano devices that people are building, whether it's for implantation or biosensors that are being used to study Alzheimer's and things like that. It will become very important. And of course, in future, maybe we will have oil and gas fields. I call that Q fields, quantum-driven fields, where we can actually have a truly integrated oil well life cycle. So these three case studies that I'll mention a little bit more in details. Why is it important? And look at this, a simple cell, or if you call it a cell from a solar cell point of view, plant leaf is a cell. Inside a plant leaf, there are roughly about 50 chloroplast molecules, and each chloroplast molecule has about 4,900 chlorophyll molecules, which is arranged in a very beautiful design of 17 by 17 by 17. And each chlorophyll molecule has roughly about 328 orbitals, so to say. That means you have a matrix that you want to actually play with, which is about 162, 1464. I just want to read those numbers, right? If you think of it, how big is this system, right? If it's a matrix of that size, it's an n-cubed problem. How much compute resources we will do? So when a quantum chemist or a physicist works on these problems with these kind of fancy-looking equations, what we try to do is take this 3-dimension picture and translate into a 2-dimension, and then convert into 1 dimension to actually able to compute, because the computing power doesn't exist. We are able to do maybe about 17 by 17 in 2-dimensional system. Beyond that, we can't. But the real world is 3-dimensional. And of course, we are talking about purely chlorophyll molecules. But imagine these chlorophyll molecules within a chloroplast is in a system, in a in vivo system, so to say, where other molecules are there. We ignore that in actually trying to build or mimic the natural solar cell. So with this kind of computation that are available with quantum computers, we will be able to actually resolve this as how that energy conversion really takes place in these natural solar cells. The chemical part is known, but in order to design a solar cell, we can actually take advantage of it. So that's why it's an interesting challenge, and I hope in my lifetime we are able to do that. The second one is DNA molecular wires that we call. And this is an example of which is actually based on a non-sparse matrix of 4,000 by 4,000 interactions or matrix. And this is just a 15 base pair DNA on the rightmost side, where there is an electron donor and an acceptor attached to it, and to study the property of it. But in real world, these DNA molecules are much larger, and they have other associated ions around it. And this creates a very interesting challenge in designing bio nanowires, whether it is proteins or whether it is DNA. And when you combine these biomolecules, you can design some beautifully architected bio devices. And there's many people are doing experimental work, but in order to understand the underlying principles, the quantum computing is essential now. The third one, as I said, is the Q field. So this is just an artistic rendition of a future field, so to say, where everything looks digital. And this is where actually, if you look at concepts like reservoir simulation that goes in, the seismic data analysis that goes into the oil and gas industry, if all the data is combined in, so to say, real time and actually applied while the operations are going on, and that itself becomes multidimensional, multivariate challenge, which can actually take advantage of extensive computing resources that could be available from a quantum computer point of view. But these all require challenges to convert all these problems into what is called the qubit problems, as I call it. But this can be done, and people are now working in that area. Because typically what you have is you formulate a physical problem or a biological problem, like as I discussed earlier, into a qubit formulation. and then you define what the initial state would be and what is the final state we are looking at, and then you actually leverage the computing power of it. Of course, there are various methods for quantum computing. There are a lot of literature available. My goal is not to give you a lecture on those things, but there are three main methods: quantum annealing, analog quantum, and universal quantum computers. Each one have their advantage, disadvantages, scalability issues, actual manufacturing or building of these computers, but each have their own strengths and weaknesses. So when we are talking about different use cases, as an example, I said, we may have to look at the right combinations of these quantum computers. With that, I think that will be my last slide. I thank all of you. One is, as Industry 4.0, and we go beyond it, the interaction between human and machine-to-machine interactions will grow and will be important. Hence, this overlap with quantum computing becomes critical for us. With that, thank you very much. I hope it was a useful session for all of you. Catherine, we can't hear you. Catherine, I couldn't hear you.
Hi, Satyam. I'll jump in with the Q&A in the meantime. Can you hear me okay?
I can hear you fine.
Okay, wonderful. I'll jump in. Oh, there's Catherine. I'll turn it to her.
There we go. It wouldn't be a live event if we didn't have some technical issues. That's how you know it's authentic. So let's dive straight into one of the first questions we have here. So Satyam, in your opinion, how prevalent will quantum computing become in the coming years? I think to kind of preface this question, I think it's always interesting. You see big data, AI, machine learning, they've gone through that evolution of being buzzwords, being on every conference in town, through to kind of the hard work now commencing. So where do you think quantum computing currently is?
So interestingly, quantum computing has been there for some time. The term has been there and people have actually started building things. But I think there is a lot of activity in last, I'd say, 3-4 years. A bunch of companies have actually had some great successes, right? Of course, the actual hardware of these quantum computers is very expensive and it has to be work at a very low temperature, so to say. And so investment hasn't been there. I think today, if I read the articles right, Canada is #1 in investing in quantum computing. So now as a country, that is important for them, which is great. And so there are a bunch of companies now, even in US and other places, that are investing in it. So I think I would say we should see a much better exponential growth in the next 5 years.
Brilliant. And that just kind of picking up on that point that you make about it being kind of almost, there's a barrier there due to the infrastructure of being so expensive. What would be your suggestion for someone that thinks that, you know, quantum computing could really benefit their industry and their company and their organization? What sort of conversations would you look to be having with the C-suite to really get that buy-in for that journey?
Yeah, that's a good question, because, you know, depending on the company, whether they are looking at a short-term return on investment, or are they looking at long-term return on investment and larger return on investment through innovation. So it depends on the company's strategy and the leadership, how they want to think about it. But I think what companies should look at it, how much of a player they want to be in a certain industry, right? So if you're talking about, say, energy industry, whether you are a renewable energy player or whether you are a traditional energy player, right, whether you want to be a big player of that market share, or you want to be a bigger player going 5 years from now, 10 years from now. And so your investment decisions will come from that that kind of a decision-making process. And if you decide, no, my core strength is only traditional energy, and if my market share is declining, I don't want to do much about it, then you really won't do it. But I think if you are a progressive, forward-thinking company, I think you will invest in this area.
Fantastic. And we've had a question come in here very similar to that kind of area. So just kind of want to highlight that of this question says, what steps can I take to ensure my organization is ready for this transformation? So, you're taking stock of the environment and kind of saying, where do I want to be in this game? But are there any other kind of key factors that you think you need to be ready to start this journey?
No, I think the number resources, we have challenges with the traditional artificial intelligence, machine learning people, right? And of course, there are a lot of activity going on in that space. But with quantum computing, you have one extra dimension, because these people have to understand the quantum physics or the quantum chemistry as well, because you are taking a physical, biological, manufacturing, engineering problem and actually trying to convert into a qubit problem, right? So to say.
Yeah.
And that without that knowledge, it's not easy. It's not that you can just build. Anybody can write a code in Python and you're done.
Makes perfect sense. Now, earlier you did touch on cybercrime and attacks. We've had a question come in here saying, with attacks becoming more prevalent than ever, what part do you think quantum computing can truly play in reducing these attacks? On another session I was recently on, it was quoted, it's not about if you get these attacks, whether it be data poisoning or data manipulation, it's a case of when. So what role do you think quantum computing can truly play in that?
I think a couple of things, right? One example is that with quantum computing, encryption, cryptography becomes very powerful. So you can at least protect your assets. So the loss is minimal, right? Second is, if and when these computers are mature, one can analyze the attack data much faster, or in a real-time sense, and prevent it from happening high-scale or large-scale attacks. That's another area. The third would be like just historical data that we can analyze. Typically what happens today, only maybe a few agencies will look at historical data, but or few companies are looking, who are building some solutions, but most of the industry is not looking at what has happened in the past. Because they're fighting the present, right? So I think that could be that people can actually build more insights from the past data as well.
Fantastic. Right, let's dive into the next question. Thank you guys for sending these in. We do still have a bit of time, so do keep sending them in to us. What do you think is progress in terms of quantum computing for common users?
That's a tough question in the sense, because one is to define common users, right? As I said, I would have called myself a common user 25 years ago, but we had no progress then. But I think certainly in the last 5 years, we see some more significant progress. And a lot of work is going on in terms of converting the challenges and problems that can be implemented on the quantum computers, but it still requires a little bit more work than we won't have citizen quantum engineers yet, as like a citizen data scientist we talk about in the AI world, but certainly we would have a lot more quantum computing experts in like next 5 years.
Brilliant. Fantastic. So we've got a few more moments here. So let's take one more question. What is the first challenge in transforming computational challenges for quantum computers?
Yeah, I think I touched upon that a couple of times now. So I think it's more about understanding the real physical and technical and manufacturing problems, and then how do I actually translate it into this qubit problem, so to say, right? Because it requires a different kind of thinking, that you're trying to describe two state, but you have a combination of 4 state to define 2 state, right? So you are actually, in some sense, increasing your increasing number of states with the 2 to the power n to actually describe a simple n state. So I think that itself is a challenge, and saying, why do I want to expand the problem? I want to reduce the problem. So that mindset is required.
Fantastic. Now I'm looking at my clock, and I think that's all we have time for today, Satyam. Thank you so much for joining us. That was an absolutely fantastic and fascinating session. Thank you so much.
Thank you, Catherine. Thank you, April. Bye now.